plus h minus 10 squared, be careful, you have to square the whole quantity, equals 10 squared, which is 100. And we have some choices here, all right? We're either going to solve this thing for r, or we're going to solve this thing for h. Do you agree? Do you all have a preference? R and H, two different. Does someone want to give an argument as to one way, why one way might be better than the other? So if you have a domain restriction on R that you're comfortable with, then solving this thing for H would be good, because then you could easily substitute in. Okay, that's a good argument for solving that thing for H. Who has a good argument for solving it for R? I have one. Anyone have? I have one.
You could plug it in.
What is in the formula?
R squared.
R squared. How easy would it be to solve that for R squared? Pretty easy, right? Now, then I have to deal with the domain on H, using H. But H is just the height of this cone, right? And the height of the cone can never go past the diameter of this sphere. So I think I'm okay with that sort of domain thing. Now, it can be done both ways. I mean, you get the same answer no matter which way you do it. But I think I like the idea of that thing being right there and just moving this over. Okay, so I'm going to go for r squared here. Not even going to take the square root. 100 minus h minus 10, that quantity squared. So that gets plugged in over there. So now my volume of my cone is equal to 1/3 pi r squared, which is this, all of that times h. Is our volume a function of a single variable now? It is. Okay, what I'm going to do next, I'm going to go ahead and expand that out. I'm going to multiply that out, and then I'm going to distribute the negative through. So I'm going to have 100. I'm going to have minus h squared. Let's see, I'm going to have minus 100, then plus, so plus 100h, and then minus 100. No, 20, yeah. Thank you. Okay, so all I did was squared that, and then after squared it, distributed the negative through, came up with this. And that actually works out pretty nice, doesn't it? Because those hundreds are going to be gone. And then I'm going to pass the h through. This h is going to go through and make that a cubed and make that a squared. And we're going to have our final little volume formula here, the objective function, our volume as a function of h, which is 1/3 pi times negative h cubed plus 20h squared. I think I'll go one more step before I do anything else. Minus 1/3 pi h cubed plus 20/3 pi h squared. So the reason I did that is because I'm just going to, I see that this is a polynomial, and I can just take the derivative easily once everything's expanded out. That all right? Any questions? And now, domain. So we would go back and we would talk about David's domain, right? But we've switched our variable over, so we have to look at h. Yes, Al?
I'm concerned about that negative there, because would that generate a negative outcome, or I'm a bit ahead of my problem?
Yeah, so you're concerned that we would get a negative volume, right? So this function has no idea that we're talking about a volume right now, right? Like algebraically, this is just a third degree polynomial, right? So if you think about what a third degree polynomial looks like, because it's third degree, we know it either looks like this or like this, right? Okay, now the fact that this is negative means it looks like this, right? Now, so it's going to go up on the left and down on the right, and it may have some undulations in there. We are only concerned about what happens between h's 0 to 20 because, remember, our restriction on our cone is from there. So I'm going to graph it because I want you to see it. You're asking a good question. I want to graph this. So if I do negative pi over 3 times x cubed and then plus 20 pi over 3 x squared. There it is. Jeez. It's way up there. There we go. Okay, Al. So our volume function is indeed a third degree polynomial. And yes, it does get negative answers out. But where are those negative answers occurring? They're occurring once you get past 20. So what happens is once you get past 20, then what you would get is a negative volume. And that would be when we had that quantity h minus 10. Remember that from that triangle? When you get past 20, this is going to start to contribute a negative value in there. You have to look at the whole formula together, though. It's hard to look at just one aspect of it. But the graph actually, I mean, the graph is only valid, okay, for us between here and here. After that, the geometry doesn't work out anymore, and this is not the function we need to be looking at. Does that answer your question? Okay. Yes?
At the maximum value, would that be the maximum value for h there?
Where this?
Yeah.
That's actually the maximum volume of the cone that we can get right there. And it happens when h is 13.33. But we haven't figured that out yet. We're about to figure that out. All right, so we've got our function. Now let's talk about domain. The restriction on h, if we go back and look at the picture, is that h was between 0 and 20. Do we all understand that part? Because h was the distance from the top of the cone down to the bottom, and you can't punch your cone out the bottom side of the sphere. So this is the diameter of the sphere. All right, now this closed interval method, so we're going to take a derivative now. So when we take our derivative, that's a very nice derivative compared to the last one, right? Okay, 3 comes out, so we just get negative pi h squared. And then 2 comes out, so plus 40 over 3 pi h. Yes? Okay, we need to set that to 0. We set that to 0, and that's actually going to be really, really nice to do. Because that, even though it's a quadratic, both terms have h, so we can get a GCF out. And the GCF we can actually pull that pi out of there. I'm going to pull a negative pi out. Negative pi h comes out. I'll be left with h minus 40 thirds. And that is it, right? And now you set each of these equal to 0. So the only time this is 0 is if what? H is 0, right? And then you set that to 0 and you get h is 40 thirds, which is 11.33333, right? Oh, 13, sorry. 13.33333. Yeah? Now, we have not shown that this is a max or min yet or anything, right? We actually now have to plug in to our original function, right, into this. We need the volume where? At 0, the volume at 20, and the volume at 40 over 3. And when you do that, the volume at 0 is 0. You can do that, you can see in there. And I think the volume at 20 is 0. No, 0, not 20. And then the volume at 40 thirds, I can cheat because I already had the computer do that for me. It was 1241.123. So this is obviously where we have a max, right? So have we answered the question?
That's to the original function?
Pardon? The original, yeah, because remember, closed interval method, your points go in the original.
So you're really just finding a max or a minimum of the function.
Of a function. So in theory, like real world, if you could just come up with a function and go to a computer and graph it, you'd be done, right?
Yeah.
And that's the way it would be used in a real world application most of the time. Is like the problem for the engineer is to come up with a function. Like you need to generate the function that gives you the volume, and then max and min of it, you just look at the graph.
Okay.
Yeah?
So most of optimization is just finding a maximum or a minimum.
All of optimization is finding max or mins. Yep. Yep. That's all it is. All right. So I think I've given you enough problems for you to go and suffer through the homework. Every problem is going to be, like I said, very unique. The algebra, the geometry. Oh, we didn't get the, sorry, we didn't answer the question. I'm sorry, I got distracted. We found the h value, right? H was 40 thirds. That's where we get a max. But it asked for the dimensions, so we need r also. So what's the radius of the cone? So we have to go back to our formula for radius, which we got from our triangle. We actually got this, right? 100 h minus 10 squared. So what we would have to do is plug that in for h, and then do all that, and then square root it, and that would be your radius. I'll let you do that on your own. Okay. I just randomly pulled up a problem from a way old, that's 2010. 2010 Cal 1 final exam. And I guess I gave up an optimization problem where it had to do with a box. That's a problem that you'll find that in your homework, a problem like that, okay? Just to give you an idea of a problem I've asked before. Let me see if I can find another final. Here's one from spring 18. Let's see here. Find where function's decreasing. Where's my, what's that?
Not posted?
No. That's not a final. Oh, look at that, it's a related rate problem. Oh, there we go. I gave a barn problem. That's an optimization problem right there. So I guess what I'm getting at is there's really no one thing that you should know for the final. It's make sure you do your homework, Make sure you understand how each of those problems, is worked. And hopefully when you get to the final, you'll have it, you'll be ready. Yes? Okay, let's get to that unsolved problem. That I went to the computer earlier to solve it, right? Yeah? So I want you to consider the following idea. This is actually the next section in the book. It's called Newton's method, but I don't want to formally introduce that yet. I just want you to look at this first. Let's say we have a function. And let's say, just to make this go very nicely for me, let's say that our function does something like that, right? This is a function f of x. Now, we know that if you say, hey, where is f of x equal to 0? You're asking for the x-intercepts of the function. That means that you want to try and find this point, right? So here's a very strange but clever way you could find it. How about what I do is I just take a guess first. All right, so let's just say for the sake of this problem that this is the number 1, okay? The solution is 1, but we don't know that, okay? We don't know the answer is 1. So let's say I make a guess, and I try to guess the point, 2. Say, okay, I think 2 is the answer. How could I check to see whether or not 2 is right? Plug 2 into the function and see if it spits out 0, right? So what would happen? If I plug 2 in, it's going to come up here, it's going to spit this out, right? And that fails because f of 2 is not 0. So then what I'm going to do is I'm going to try and see if I can get to this point by drawing a tangent line at that point and seeing where it hits the x-axis. Okay? Where I hit the x-axis is my next guess. So now I'm going to try this answer and plug it into the function. And what's going to happen? It's going to come out and it's going to be positive, right? Then what? Do it again. Take the slope of the tangent line, right? Take that tangent line and follow it down to the x-axis. And then take that point and take a guess. Plug it in, right? And then do the slope of the tangent line again. And what's happening is that these tangent lines, where they hit the x-axis, are slowly marching towards, not slowly, I shouldn't say that, they are rapidly approaching the solution. Now, will I ever get there? What's going to happen is as I continue this procedure over and over, my outputs are going to start getting smaller and smaller and smaller, and they're going to start to approach 0, basically. And so what I'll do is I'll just run this. I'm going to run this like an algorithm, like a do loop, okay, on a computer. And I'm just going to keep having it try a number, then come up with this new point, and then try that, and come up with this new point, and try that. And I'm going to do it until the answer that's coming out, this height, is within some predetermined tolerance. Let's say I say, as soon as that number coming out is like smaller than 0.00000001, stop, end the loop and spit out, there's your, this point that we're at is our answer. And that's what just happened on that computer. All right, it's Newton's method. So let's see if we can come up with the algorithm, okay? Because I think you would agree, hopefully you would agree, that the first point that I picked here was just truly a guess, right? So let's just start the idea of this algorithm by saying, let x sub 0 be equal to c. And c is just going to be some constant, all right? This is our guess. All right, so we're going to plug that in, right? This is our x naught. We're going to plug that in. It's going to go up here. And then this is the hardest part of the whole thing, is how do we figure out this point? How do we figure out that point? The what? Oh yeah, and also we know the function, okay? The function has been given to us. We have the function. We have it, all right? So the derivative of that function is not this point, right? The derivative of that function is what? The slope of the tangent line. The slope of the tangent line is not that point, right? Would you agree that this point is the x-intercept of the equation of the tangent line? Say that again. This point is the x-intercept of the equation of the tangent line at that point. Okay, so let's figure out what the equation of this first red line is. I'm going to have to do this on the side. So maybe you can help me out. I have a point here. What's the point? What is the x and y coordinate right there? Well, I plugged in x sub 0, right? Which was some guess. And the y coordinate is what? The function's value at x sub 0. Do you all agree with that? That's that point. So I have a point on this line, don't I? I have a point on the red line. Do I have the slope of the red line? What's the slope of the red line? The derivative of the function at this point, right? So this is a point on the line. The slope of the line is the derivative of that function at that point. So if somebody gives you a point on the line and they give you the slope of the line, you can come up with the equation of the line. So what is the equation of that first red line? What's the equation of this first red line? Y minus, what's y1? This coordinate, right? This one. So f of x naught, okay, equals the slope f prime of x naught, okay, times, in parentheses, x minus x naught. This is the equation of the tangent line at x equals x naught. That's the equation of the red line. Do you agree? But I'm not looking for the equation of the red line. I'm looking for that point, which is the x-intercept of that line. So what's the x-intercept of that line? How do we find x-intercepts of lines? Plug in 0 for y, right? So now if I want to find the x-intercept of that, I'm going to replace y with 0. Okay, if I replace y with 0, then here's what I get. Negative f of x naught equals f prime of x naught times x minus x naught. Right? All I'm doing is replacing that right there. Right? With 0. And now we're going to take this and solve this for x. Because this, right, this point right here, this x, that's what I'm trying to figure out. What is that x value? Well, x naught's over here, right? But everything else is in terms of x naught. So let's get this x by itself. So how about first we divide this thing out. So I have negative f of x naught over f prime of x naught equals x minus x naught. One more step and we'll have x. Add x to both sides. So I'm going to add, sorry, x naught. Add x naught here, add x naught over here. And what we get is a formula for x naught, right? So here it is. Or sorry, a formula for x. We get x is equal to x naught minus f of x naught over the derivative at x naught. So if somebody gives you x naught, right, or you start with a guess, x naught, and you give me that x naught, it's going to go in here, it's going to create a tangent line, and then we are going to find the x value of that, and that's what it is, right? So this x value that we just get here just requires x naught. X naught goes in, we've got the new x value. This new x value is going to be my next guess, right? So I'm going to call this next guess x sub 1. See, this was x sub 0. This is the initial guess. And having that initial guess spits out the second number, x sub 1, which is going to be my next guess. And I'm going to run it through the same algorithm, right? So I'm going to come back over here and I'm going to change this to x sub 1. And if we're going to run this same algorithm over again, then I can come up with a general formula based on this same principle, which would read as follows. The n plus 1 x value, so this is our first one, right? Our 0, 1. This is going to start marching over, and these are going to start piling up in here. If we want to know what the value of the n plus 1 x value is, it's going to be equal to the one before it, right? The one before it, just like this formula says. If we want to know this one, I got to know the one before it minus the derivative, the function at the one before it over the derivative of the function at the one before it. And this right here is what would need to basically be programmed into the computer. It's basically what we call a recursive function. So you give it an initial state, and then it's going to run through this thing. It's going to have to do these checks and stuff to see like when to stop the program, but that's basically what's happening. Does that make sense? So when you type that in, it's into the computer, it's running through this thing called Newton's method. I have 12 minutes. So let's see if we can't do this to solve that problem we just had. So you can see this in action. So what was the equation we had? It was y cubed minus 3y was plus 8? It was minus 8? Okay. Now I changed the y's to x's. Is that okay? Right? We were trying to solve that equation? What was the answer? 2.4? Are you sure that it's minus 8? Yes. Yes, it is? Okay. Okay. 2.5? Okay. I thought it was 1.5. That's why I was like, wait a minute, this isn't going to work. All right, so right now, we are going to try and see if we can't come up with a guess first. All right, a guess. So a guess would be, we just kind of think about this. What if we plug in 1? We get 1. We get minus 3, minus 8. That's pretty far away from 0, isn't it? Okay, let's try 2. 8, right? 2 cubed, 8. So if I let x be 2, I get 8 minus 3 times 2 is 6, right? Minus 8, and that's going to be negative 6. That's still kind of far from 0. Maybe we try 3. So what if x is 3? We get 27 minus 9 minus 8. What's that? It's not much better, is it? What's that? 10? I don't know. I mean, 2 seems to be like that might be our best choice, right? 2 is pretty close. I don't know. Doesn't matter where you start, really. Okay? Well, it does, but for this problem, it doesn't.
Use a fraction.
Oh, yeah, you could use a fraction. But the thing is, the algorithm itself should take us to the answer. So we don't have to be super, super close. We just need to be close enough. So why don't we go with 3? Because 3 is still pretty far away. Let's just see how fast we can get to the answer. All right, how much time do I have? 10 minutes. Okay, here we go. This is the formula I'm going to use, right? This is it right here. I'm going to write down what the function is, just so we're all clear. The function we're using here is the left side of that equation, which was x cubed minus 3x minus 8, right? That's the left side. And I'm going to need its derivative throughout this process, so 3x squared minus 3. Somebody have a calculator handy. There's the function, there's its derivative. I need them because in the formula I'm using the function and the derivative. So here we go. Start with the first one. Our initial point, our initial guess is us plugging in 3. Okay. Now, how do we get the next point? The next point will be, according to this formula, it'll be x sub 0 minus f of x sub 0 over the derivative at x sub 0. Right? That's what it is. So that should be x sub 0, which is 3, minus f of 3 over f prime of 3, which should be 3 minus, that f of 3 was 10, we calculated that earlier, over the derivative at 3. 24. Okay, somebody on their calculator, give me that as a decimal approximation. 3 minus 10 over 24. 2.5833? Okay, all right, that's our second point. Now let's go again. Let's find the next point. So what we've done is we basically picked a point, we just went up, boom, boom, and came and just got this point. And now we're going to do it again, boom, boom, and get another one. And just keep marching towards the x-intercept. So our second point, and the boom, boom, it doesn't have to sound like that. Sometimes it's bam, boom. Or bing bang, that's irrelevant. Okay, so I'm just repeating the formula, right? But now I'm using the other point that I just got. So to find the third point in this sequence, I'm going to use the previous point that I just found. So now I'm going to need my calculator. So this will be, do it here. I'll do it here. This is going to be 2.5833 minus the function evaluated at 2.5833 over the derivative at 2.5833. And so this seems very tedious, doesn't it? This is a lot of like computations. What's really good at computations? Computers, right? This is perfect for a computer. How fast could a computer run through this? Right? You get this answer, you store it, and then you call it, and then you get a new answer, and you store it, and you call it, and you just, I mean, it's... Okay, so does anyone have this one? Approximately 2.495. Okay, so you get the idea, right? Got to find this real quick. I programmed it in here a while back. Newton's method. Okay, here we go. Open, darn it. It's not a pretty little program here, but I can't see because there's a glare. There we go. X, can you all see that? That's my function, x cubed minus 3x plus 8, or minus 8. Okay, that's the function. And this right here is my guess. And we started at what, 3? Right? Was it 3 we started at? Yes. Okay, so now I'm going to run this, and I'll erase all that stuff. There it is. Okay, so when we ran it, that algorithm, right, when we were running it, the first number we got was 2.58333, right? The second time we ran it, someone got 2.495. The third time, 2.492040 something, right? So this is 1, 2, 3. This is the fourth iteration. Look at the fourth iteration. Now let me bring up, I still have 4 minutes. Let me bring up Wolfram Alpha again. Maybe. Wolfram Alpha should still have our answer there. More digits. And ask Wolfram Alpha for more digits. So basically, I'm asking it to run that algorithm a little bit more for me. And it doesn't want to respond because it doesn't like the fact that I have Desmos open. Wow. What's going on here? Just going to reevaluate it. Whoa, what is that? Solve. Maybe it is real. Oh, there we go. Okay. So do y'all see what Wolfram Alpha is telling us? See what my algorithm is telling us? All right. All right. This is Wolfram Alpha. Wolfram Alpha is saying that the answer, the solution is precise up to that decimal point. Right? How good is our approximation so far? We've only run this algorithm really only 3 loops. So we've got it all the way out. We're matching all the way up to here, right? That's pretty good. In fact, I think it's only stopping there because I told it to stop at 10 digits. Let me have it stop at 30 instead. So how close are we on this last one? We got 1, 1, 1. You see that? And it's actually 117, right? So how do I fix it? I'm just going to run the algorithm a couple more times. How about I run it, we think 8 times? Something is, we should be changing more. I have the same equation typed up there, don't I? Yeah. See this right here? Okay, I see the problem. Wolfram Alpha is rounding, sorry. Wolfram Alpha is stopping here and rounding that to a 2. Sorry, I didn't see that. Right, so we basically matched up with Wolfram Alpha after right here. See that? It's pretty cool, right? It's pretty cool. Now Newton's method is a little dangerous because if you get a function that behaves in a weird way, like sometimes you can get like a sine function, and if your guess is in the wrong place, then what happens is you follow that tangent line over here, and then you wind up going over here, and then that one takes you and you're like going back, and then that one takes you and you go wind up there. So if the function is appropriately wiggly and crazy, then you'll have all sorts of problems. So what Wolfram Alpha actually does is some combination of a few different techniques. Do you remember that bisection method where I told you like you can check if the function was like positive and negative, then you know it has to go through the x-axis? It'll do something like that first. And it'll say, oh, I've got something happening in here. I have an x-intercept in here. And then it'll pick a test point in there. And it'll keep itself in there. It says, oh, if for some reason we go out of that interval, do a different test point. So, all right, that's it. We're done. Make sure you practice all of your homework for